Okay, so I'm going to get my screen ready to share. Okay, Elizabeth, and I am going to go ahead and share my screen, and you tell me if you can see it. Okay. Okay, Elizabeth, are you able to see? Let me just do a test on here. Are you able to see my writing on there, Elizabeth? Okay, great. And am I coming through clear? Is it pretty clear for you? Okay, wonderful, Elizabeth. So I realize that you have a question, and your question is, how do we determine the multiple answers for sine squared of 2x, quantity 2x, equals to a value of 3/4? Is that correct, Elizabeth? That's supposed to be a 2x. It was just sine squared. Okay, so it was not sine. Okay, so it was sine squared of x. Okay, so sorry about that. Let me erase this, and we have sine squared of x. Do we agree so far? Oh, so do we agree? Do we agree so far? Wonderful, wonderful. Okay, so the first thing, let's go ahead and work this through. But let's go ahead and let's forget the trig for right now. So let's go ahead and forget the trig right now. Let us say that I gave you an equation u squared equals to 3/4. Let's say I gave you u squared equals to 3/4. Do you agree that in order for me to solve for u, I would take the square root of both sides, Elizabeth? Great. So when I take the square root of both sides, remember, in this circumstance, I'm going to get a positive and a negative. So solving here, I would get both plus or minus square root of 3 all over square root of 4. And remember, square root of 4 is just equal to a value of 2. So solving this, I would get u equals to plus or minus square root of 3 all over 2. Do you agree so far if we were solving for the random equation u squared equals to 3/4? Okay, wonderful. So now let's transcend into trig. Let's transcend into trig. So if I wanted to get rid of this square with the sign, what could I do? What is the opposite of squaring something? What would I do to get rid of that square? What's the opposite of the squaring something? Do you agree it's taking the square root? Perfect. Yeah, that's the exact same thing. The same thing we had here with u squared is the same thing when we see sine squared. So if I want to solve for just sine, I'm going to go ahead and take the square root of both sides. I'm going to take the square root of both sides. But remember, just like we did here, just like what we did here, we have to add, we're going to have to add the plus or minus to our solution. So we're going to have to add the plus or minus to our solution. So we know sine of x is equal to plus or minus square root of 3 all over a value of 2. Do you agree so far? Okay, wonderful. So now we've tackled the first, I'd say 30% of this problem. Let us continue through and remember some things about our sine curve. So let's think about sine. So I'm going to go ahead and draw us the sine curve between 0 and 2 pi. And I know you didn't say it in the question, but hopefully in the question, does it give a domain or restriction between 0 and 2 pi, Elizabeth? Yeah, okay, so that's what I figured. This actually, because our sine graphs are forever, they never end. So ultimately, I'm just going to show it in red, or we'll show it in blue. Normally, this graph keeps going, so it goes back here, it goes back all the way to negative infinity, it keeps going, and it would continue on past 2 pi. So we would have these periods that would continue on forever and ever and ever. But this question is just going to limit us. It's just going to limit us between 0 and 2 pi. So I'm going to get rid of those other extremes. So, Elizabeth, I hope we all agree. I hope we all agree that this value is going to be 0. This value is going to be 2 pi. If we take 0 and 2 pi and go halfway, we're going to take 2 pi divided by 2. So we're just going to have a value of pi right here. Halfway between 0 and pi gives us pi over 2. And then halfway between pi and 2 pi's is 3 pi's over 2. Do you agree those are my critical points for my sine curve, for sine of x curve? Wonderful. So if we look at this, let's think about this in terms of our graph on our Cartesian plane. Notice this is 0, this is pi over 2, this is pi, this is 3 pi's over 2, and if we go one complete revolution, we're back to a value of 2 pi. So in this circumstance, Elizabeth, do you see how at pi over 2, between 0 and pi over 2, we are above the x-axis, so we're positive? Good. And then also between pi over 2 and pi, we're still above the x-axis, so we're still positive, correct? Great. So in this circumstance, we know sine is positive in quadrants 1. This is quadrant 1. And this will be quadrant 2. So sine's positive in quadrant 1 and quadrant 2. Because we have to recognize this, we need to figure out when sine of x is equal to positive square root of 3 over 2. But we also have to figure out when sine of x is equal to negative square root of 3 over 2. So where is pi negative, Elizabeth? Between pi and 3 pi over 2, pi and 3 pi over 2, it's negative. And then he's also negative between 3 pi over 2 and... Excellent job, Elizabeth. Exactly. Quadrants 3 and 4, third and fourth quads. So we realize that he's positive in 1 and 2. He's negative in 3 and 4. So now after this original analysis, Elizabeth, how many solutions are we going to get in this equation? Perfect. Exactly 4. We realize that we're going to have an angle here. We're going to have an angle here in quadrant 1. We're going to have another angle here in quadrant 2, because this is where he's positive, and I'm going to do where he's negative. I'm going to do that in blue. So down here, he's negative in 2, so he's going to have another angle theta here, and then lastly, we're going to have another angle theta here. So let's go ahead and work with our first answer. So I'm going to analyze quadrant 1. So let's analyze quadrant 1, okay, Elizabeth? So let's think about this. So we have an angle theta, and we know we're looking for when sine of theta is equal to positive square root of 3 over 2. Sine, by definition, is equal to opposite over, do you remember what this one is? Perfect, hypotenuse. So great, hypotenuse. Drawing this on our triangle, we're going to have our opposite, which is square root of 3, over our hypotenuse, which is a value of 2. So we're going to have our opposite over our hypotenuse written in such a fashion. Okay, so now, do we recognize what type of triangle this is, Elizabeth? If this hypotenuse is 2, this leg is square root of 3, what does this leg have to be? 1. Excellent job. This leg has to be 1. Perfect, perfect, perfect. So if we go back to our perfect triangles, I always like to call them our perfect triangles, what angle here will correspond to the medium leg square root of 3? What angle corresponds to square root of 3 in a 1, 2 square root of... Excellent job. Pi's over 3. Pi's over 3. Pi over 3 is equal to 60 degrees. So we know our first solution, Elizabeth, is going to have to be what? Yeah, pi over 3, just that simple. But we know how many more solutions do we have to find? Perfect. So let's go through and work through our next one. Let's work through our next one. We'll work through it together. So we realize our next solution is going to fall in which quadrant, Elizabeth? Perfect. Second quadrant. Excellent job. So some people memorize the unit circle, and that's okay. In calculus, I don't expect you to memorize the unit circle. I know sometimes it's tough to do so. We have technology, we have a calculator, but I always like to know how everything's derived. So again, I'm going to go ahead and say this angle is theta. That angle's theta. Theta still here has to equal to, square root of 3 over 2. And I know it's positive because he falls in quadrant 2. By definition, sine is equal to opposite again over hypotenuse. Our opposite is square root of 3 over hypotenuse, which is 2. But we already know what theta is over here. We already know that theta is still going to be what, Elizabeth? Yeah, still pi over 3. But the way we name this is a little different. Remember, we start naming from this axis over here at 0 degrees all the way until we get to this angle. So our angle is not really pi over 3 here. It's going to have to be this portion that I just drew. So let's think about this. This is pi. This is pi. Pi is equivalent to 3 pi's over 3. Do you agree so far, Elizabeth? Perfect. So if this is 3 pi's over 3, and I need to subtract pi over 3 because I have to get rid of this. I don't want to go the whole way. I know the whole way from here to here is 3 pi's over 3. But I need to get rid of this pi over 3. How much of an angle do I have in red? Exact 3 pi over 3 minus pi over 3, exactly, which gives us a value of 2 pi's over 3. 3 pi's over 3 minus a pi over 3 gives us our second angle, which is 2 pi's over 3. Do you agree so far, Elizabeth? Okay, so think about this. We know that if we go this whole way, here, you know what I'm going to do? I'm going to remove my camera. So I think that sometimes slows up the connection. So I'm taking off my camera because it doesn't have to be such a heavy feed. So notice here, I want to name this angle from here. I want to name this angle from 0 degrees to our line, to our angle. So I know that this angle theta is pi over 3 that we found in this quadrant between here and here. That's pi over 3. But we name angles from 0 to the angle we're looking for. So we know this angle is going to be 3 pi's over 3 because that's equal to pi. But we subtract out pi over 3. 3 pi's over 3 minus 1 pi over 3 gives us a value of 2 pi's over 3. Do you see how we got that angle, 2 pi over 3? Great, great. Is this all coming back to you now? Oh, that's wonderful. That's such good news to hear. So we have found our first two. We found our first two angles. How many angles do we have to find now? How many more answers? How many more solutions do we have to find? Yeah, exactly. Yeah, 2 more in the third and fourth. So now let's go ahead and tackle this. And these actually are going to be a little bit faster now since we've gone back and reviewed our trig and our trig. So we know this right here. We know this is going to create a what is this angle going to create? We automatically know. Yeah, pi over 3 exactly. So this is going to be pi's over 3. This is going to be pi's over 3. So think about this. Yeah, I know what you meant. I got that. So this right here is going to be 3. This is 3 pi's over 3 because we know from 0 to pi, that's really just equivalent to 3 pi's over 3. But now we have to keep going. We have to keep going how much further? Another pi over 3. So what's 3 pi over 3 plus another pi over 3? Yep, 4 pi's over 3. Exactly. So now we have found our fourth solution. We are tackling this one step at a time. So we found our first, our second, now our third solution. Now we have to find our solution in our last quadrant. So we have to find our solution in our last quadrant. So that's going to be over here in quadrant 4. Quadrant 4. So we know we're going to create an angle here, and we're going to call this angle theta. We know this angle is theta. We know this theta is going to be equal to what again, Elizabeth? Yep, perfect. Pi over 3. So you can go about this tackling a couple different ways. I know that this right here would be 2 pi. If I go and I traverse my unit circle 360 degrees, I know that's equal to a value of 2 pi. Do you agree with that so far? Good. Do you realize, and do we agree that this is also known as 6 pi's over 3? Excellent. So I didn't go the full rotation, did I, Elizabeth? We only went from 0 all the way around to this angle. So what am I going to have to do between 6 pi over 3 and pi over 3 to find my new angle? What am I going to have to do if I want to find this angle? Yeah, perfect. We're going to subtract it out because this portion we have to subtract. We have to subtract this portion right here because we didn't go the full round of 2 pi's. We only went 90, 180, 270 plus another 30 degrees. And if we add this all up, this will be 6 pi over 3 minus pi over 3. So my new angle will in fact be 5 pi's all over 3. So now we have 1, 2, 3, 4 solutions. So what I like to do is I like to sort of line them up just to make sure that I know what I have, just to make sure I don't make any mistakes after we did all that work. So I know my first angle is going to be 2 pi's over 3. I'm sorry, my first angle is pi over 3, 2 pi over 3, 4 pi over 3, and then 5 pi over 3. So I realize I have my solutions as pi over 3, 2 pi's over 3, 4 pi's over 3, and 5 pi's over 3. So that's exactly how we're going to go about doing these problems. And the neat thing about this, if this was not limited between 0 and 2 pi, Elizabeth, this would keep going. This would keep going. So we would add a value of 2 pi to every single one of these solutions. So if I wanted to know what the solution would be over a value of 4 pi, so we're going to do 4 pi's, which is 2 revolutions, we would just take each one of these, Elizabeth, if we wanted to find what it would be over a period of 4 pi's, and we would add 2 pi to each one of these solutions. And this would give us the solution in the next 180, the next 360 degrees. But you know that's more trigonometry. We're moving into calculus, so we don't have to worry about finding that in the other quadrants and going and the other revolutions. So all we're going to have to worry about are these 4 solutions right here. Does that help you, Elizabeth? Okay, great. Do we have any other questions? No, it will not. Okay, wonderful. So Elizabeth, if I could ask you, what did you think of virtual office hours? Yeah, I know. I think a lot of people are. I'm actually trying to pilot this because I think this is really cool and can help a lot of people out. So I'll be doing this probably about 3 or 4 times a week, and then definitely on the weekends to help everyone out. So and again, if you ever need emergency office hours, please let me know, and I can always set up a quick conference and I can help you out through that too, Elizabeth. So never feel reticent to do so, because a lot of times it's better to explain this in this kind of fashion, and at least that way you can physically see this as I'm talking. So maybe FSU will pick up with my trend. Oh, wonderful. Well, let me know what else I can do for you, okay, sweetie? I hope you have a great night.